Build Science 101 is sponsored by Anderson Windows and Doors, Builder's First Source, Huber Engineered Woods, Polyguard, Sashco, and Durail.
Building Science 101. We're at the end here, my friends. We're talking about thermal, which is another word for saying insulation. Where do you want to start on this, Steve? This is a big topic.
I'm sad.
I'm a little sad too.
It's the final chapter
It is.
of our series.
These guys have held on for a long time to get here.
Hold on. And for those newcomers, go back. And I love science. Science says you got to watch every video 7 times to capture all the information.
That is true.
So I'm just going by what science says. But guess what we're talking about today? You're going to love this. One of my favorite topics. One of everybody's favorite topics.
Yeah, this is one that's talked about a lot in the building circles, right?
And it's the one that's probably the most easily understood,
Mhm.
right? Or at least the one that's the easiest to vocalize and have a conversation about.
Yeah, and before you get started, I do want to point out this was the last module for a reason, because ultimately the other control layers when it comes to the longevity of the building, which comes to the health of your pocketbook as a builder, those are more important. We like to brag about our insulation levels and what we're doing for insulation, but ultimately this is, in the scheme of things, really the least important when it comes to the durability, the resilience, the longevity of your buildings. On the other hand, this is probably the most regulated in the building. There's no building inspector out there that doesn't know your exact values for what you're doing for thermal control on your building.
Yeah, and they're noted on pretty much all the materials that are related to thermal control.
That's right.
So you don't even have to do anything. The building inspector wants to know what the U value of your windows are. It's on the sticker on the windows, or
That's
it's
right.
right on the insulation. It'll say what the R value is there. But yeah, today we're talking about thermal management. You guessed it. Thermal management, better known as insulation, right? But let's talk about what insulation does, right? When it is 70 degrees inside and it is 0 degrees outside, and if you remember earlier, what does heat do? Moves from high to low. So in this case, heat is trying to make its way out of my wall assembly. When it is 100 degrees out here and 70 degrees, heat is trying to make its way into and through my assembly to the inside, because what it wants to do is it wants to make that temperature 85 degrees somewhere, right? It's trying to equalize that temperature. So we have to put up le resistance.
Sounds French.
It does. You didn't know I speak French.
I didn't know you spoke French.
Me neither.
Le resistance.
Me neither until about 2 minutes ago. So, resistance, better known as R value.
Yep.
Right.
The amount of resistance, R value.
R stands for resistance in there. So, higher the R value, the more resistance that we get. The lower the R value, the less resistance. Now, one of the things about R value, and you probably won't be surprised to hear this, like many of our other topics of discussion, resistance is somewhat climate tuned. Right? There are places where it is in fact 70 degrees outside and 0 degrees outside a lot.
Yeah.
But there's also places where it's 70 degrees outside and 50 degrees in the winter. And it's a little bit less, right? That delta is almost somewhat equalized.
Mhm.
And if you go to places like, say, San Diego, you're pretty much equal across that wall system, or Hawaii. You're pretty much equal across that wall system for the day.
We call those temperate climates, right?
Yes.
Because the temperature is not very different between outside and in. It's temperate.
Yeah. Hawaii has a slightly higher temperature, but the wind in that just makes it feel a little bit better and helps to equalize it. But, you know, the funny thing about R value is not only is it climate tuned, but I would argue it's assembly tuned. And what I mean by that there's certainly areas where that delta is higher. So I gave the 70 and 0 example here, or 170 there. If we go down into this crawl space and or basement, and I say, this is still 70 here, but this is 55. And this is 55 here. And in the 0 degrees, yeah, maybe this is 35, a foot below grade or whatever.
Yep.
But the idea is that the delta across here and the delta across here and across here is different than the delta across there.
It's generally not as much.
Exactly. And if you look at the stack effect, well, we have a lot of very hot air accumulating here. And hot air wants to equalize. And even though this is 70, this might be, in fact, 72 degrees inside that room. And that air is trying to equalize with my 0 degree attic in some places.
Yep.
So depending on where I am in the building, depends on how much R value I put in that assembly.
Yep.
So down here, Building Science Corporation, which, we haven't mentioned it, but Building Science Corporation has a website that has an immense amount of knowledge for free.
Buildingscience.com is the website.
Buildingscience.com. And you're not going to find one-stop shopping in building science better than buildingsciencecorporation.com.
For sure.
So go there. But they have a paper that Joe wrote, and it's called the 10, 20, 40, 65 rule. At least that's what I call it. But basically what they're talking about in that paper is that the assembly tuned R values are proportional to their load. And the load is the delta across the assembly. So down here, we might need R10 and the subslab. In our basement assembly, because that temperature is getting colder, and I'm talking heating climates right now, then that wall insulation bumps up to 20. Above grade walls, we bump that up to 40. The roof system, we bump that up to 60. And then windows are R5. So you can see those numbers. Those are assembly tuned, or what I would term proportional to the delta that they're challenged by.
Now, insulation in all the areas of the house that you mentioned, Steve, except windows, resonate with me when I think R value. But for windows, you mentioned the value 5 as an R value. I always think of windows as U factor. Can you explain that difference?
Yeah, I certainly. And it's going to take us right into the next topic. But the reason windows are measured in U value is because they're not a sole component, right? Insulation is very easy. They take a piece of insulation, they put it in a hot box, they seal it up, and they measure the resistance of that material to heat flow, right? A window, if I look at it in section, right, there is a frame. The frame has pieces of plastic. It has different pieces inside. It has the IGU, which is the glazing unit. There's a spacer mechanism in there, but there's a whole different set of components that do that. So you can't measure the R value there, because it would be like trying to measure the R value of my t-shirt if I put a sweater and a jacket on, right? Because the t-shirt alone certainly has an R value or a resistance to flow. But the minute I put a sweater on, the sweater is going to slow the heat flow through my shirt. So now as I add components like the jacket, the heat is going to flow even slower through my shirt and through my sweater. So you no longer can measure the R value of a material when you're measuring the resistance of an assembly.
Okay.
Right? And we're going to talk about that again, so hold on to that. But that's why windows are measured in U values, because everything has a resistance to that heat flow.
And how do we know how U factor correlates to R value?
So it's very easy. A U value of, say, 0.20 is actually, and I picked that number because it's simple math, the U value is actually the reciprocal of the R value. So 1 over 2.0 is R5.
Got it.
right?
So-
Or R5
So a
is
0.33 window U factor
R3.
is roughly an R3 window.
Right.
Yeah.
So the lower the U value, the better the window is, or the assembly of components, whatever we're measuring by U value. The higher the R value, the better.
Yeah.
So
makes sense.
depending on what you're talking about there.
Got it.
So we talked a little bit about resistance. We talked about the proportional, but we're going to go back and we're going to bring in a thought that we talked about in air tightness.
Mm-hmm.
So Joe coined the red line test, and I'm not going to say I coined the green line test,
But you can.
but what I'm going to say is that I've taken Joe's information that he taught me and I curated it a little bit.
Okay.
And then I'm regurgitating it to the building industry and saying, just like air tightness, we need continuity in insulation. And guess what? Wherever I start, I should be able to close that green line, just like the red line test, and be in confidence that I have insulation all around my assembly.
Give me some examples of where there might be a discontinuous green line.
Well, like Joe would say also, if we could build houses without clients and windows, we could build a hell of a house. But the reality is people want windows,
Yeah.
right? So we have to put them in. Well, what does that mean? It means that I've interrupted my air barrier, my weather resistive barrier. I've interrupted pretty much everything, but I've also interrupted my thermal barrier. And whether I believe it or not, the window now is my thermal barrier,
That's right.
or component of my thermal barrier. And now all of the pieces that bridge that window unit through the rough opening to my thermal barrier in the wall are also components of my thermal management system. And that's why I keep talking about these things as a system, because we have to dispel the myth of thinking of, well, my thermal management is the insulation. No, it really isn't, because at some points in the wall, it could be the stud work, the king and the jack frame that are adjacent to that rough opening. There's no insulation there.
Yep.
But they still have an R value in a 2x6 of like 5.8.
Yeah.
So there's a little bit of R value there, but it is still, even though it's not insulation, they have thermal properties. The same with windows. Glass is horrible, but we can add films to the glass to enhance the insulative properties. We can space the glass and seal in gases like argon or krypton, which add to the insulating value of that IGU. So there's a lot of components that make up this thermal management system. So you really, as an architect, you need to get your head around the idea that we're not just talking about insulation. Yeah, it's real easy to sit there and say, hey, put R21 in the wall. But you really need to understand, well, what happens down here when the wall stops? What happens with the insulation here? Is that the same as insulation on this wall? Is that the same as the insulation underneath my slab?
That's right.
Chances are it probably isn't.
Yeah.
And there's a lot of choices. It's not just one choice. Like, okay, we're going to put a 20-pound XPS rigid foam R5 under the slab all the time. No, there's other options that we can put under there.
Yeah,
There's companies that make graphite infused EPS, polyiso, all these stuff. You can spray foam down there. There's a lot of options. So like every other decision that's going in this house, you need to climate tune your thermal management system, and you also need to assembly tune that system.
That's a great point. One thing I might recommend as we're thinking about this green line test, if you are a student or a young builder who's not spent any time with an infrared gun, this can be really valuable in your understanding of this concept. You know, Steve mentioned that studs, 2x4s and 2x6s have an R value of approximately 1 per inch. And if you look at that wall behind Steve here at our Rockwool studios, that Rockwool insulation in that stud bay, it's a 2x4 bay, is roughly R15. It's got a resistance of an R15 value. The stud, that's a 2x4 stud, maybe a 3 or R4 value. If I were to look at that wall from an infrared camera, on a cold day outside, those studs would be transferring a fair amount of heat from the inside of the house outward, and they would actually look cold on the infrared camera as compared to the stud bays that have those rock-wool bats on them, which would look warmer because they're keeping things warmer on the inside of the house on a cold day outside. If, on the other hand, we looked at a commercial building, and a lot of commercial buildings use steel studs on their walls. Steel is a good conductor of heat flow. You know, we don't make electrical wiring out of wood. We make electrical wiring out of copper or maybe even aluminum. So steel studs can conduct a fair amount of heat. And as a matter of fact, that's something that commercial builders have to really think heavily about, is that heat flow, because there's really good movement of heat through steel studs. So they have to do other things that insulate besides just cavity insulation. Same is true with, glass buildings. Glass buildings don't have a lot of resistance to heat flow. As we talked about earlier, the U factor, and in fact, in Steve's example here, we're looking for R5 glass. Ideally, that's not actually all that common in America. Most of the time in America, probably including Canada, a lot of the glass that's in new construction is somewhere around 0.27 to 0.33 U factor. So it's, at best an R3 glass. And that's true with, big commercial buildings as well. So as we think about this thermal resistance, thermal management, there's a lot to think about. And that infrared camera, if you can borrow one, rent one, if you happen to be watching this in a classroom, that could be a great field study for you and your classroom to go out there and look at some various buildings through that infrared camera and see what those images look like.
You couldn't have done a better transition to my next concept.
I love it. What do we got?
So we're going to do some myth busting here.
Ooh, very
I'm going
cool.
to call out some people, and I'm going to call them liars.
Okay, wow.
I switched the color here, all right? So I sit down at a table with 3 builders. I ask builder number 1, what kind of house does he build thermally? He says, you know what, Steve, we build the code R21 walls. So, okay. Builder number 2, you're a little bit better of a builder. He goes, of course, yeah, we build an enhanced wall system. We're right around R30. The third builder, before I even ask the question, he throws out his chest, Steve, I built nothing less than an R48 wall. I look at all 3 of them and I say, every one of you is a liar, and I'm going to prove it to you.
All right, let's hear.
So if we look at the components of the wall, which you just did, I'm just going to graphically illustrate it. I switched the color because I'm just going to draw over.
Okay.
If we draw a wall that has the stud work in there, and it marches across, and then we put a window in.
Yep.
There's actually 3 parts to that wall system, right? There's what I call the opaque area, and that's where the framing is.
Yep.
There is the cavity area, and that's where there is no opaque or no wood, and that's where I'm putting insulation. That's where they're telling the truth.
Yep.
So when they tell me R21, R32, R48, what they're citing is the center of cavity, the COC, and that's the R value that they're citing. Well, like you just talked about, in North America, most of our windows will just say they're 0.3, right? Or R3.
Okay.
They're in that ballpark. Now, as I march across that wall system, we're going to understand that in the house, about 20% of my wall system is windows and doors. The framing, whether I do advanced framing or not, I'm just going to keep it real easy and say that we're probably at 15%. So that's 35%. So that means the remaining cavity.
That'd be as if, Steve, you stacked all those studs.
We took them, split them all to one side, and then we took all the glass and homogenized it into one window.
Okay, understood.
On the whole house.
Yep.
That cavity now is 65%.
Yep.
So when the 3 gentlemen in my conversation say I'm building 21, 32, and 48, what they're really suggesting is That's what they fill their cavity with. But if I take their numbers, we'll take the R21, for example, and we normalize it against 65%, that 15% in framing is probably, let's say, R5.5
Yep.
for a 2x6. And the windows are R3, right? That guy that's building the R21 wall, he is building probably somewhere around R11 to R12 at best. That's the house he's built.
That doesn't even meet code in climate zone 1 or 2 where I'm building.
It doesn't. But the code is suggesting the cavity resistance,
Just cavity resistance.
not the whole house
Yeah.
R value or whole house resistance. The guy that's doing the R32, yeah, he might get a little bit of a bump and be building R14. And of course, the R48, he might be closer to like R18, R20.
Mm-hmm.
But the reality is that the center of cavity is not the whole system. Now, the last piece to that is I can't really enhance the windows by adding something to it. I just have to swap out and buy a better window.
Yep.
Right. And there are companies that have, you can get triple glazed windows from domestic manufacturers. We can import them. They're all around, but you could check out that U value. The best I know of is probably somewhere as a whole assembly unit, probably in a 7.5, 7.7 range is about the best you're going to do without getting crazy about it. There is something I can do to this 15% framing, right? If I have a wall system here where I have exterior sheathing and I have my stud and my stud, well, this, like I said, this is at our 5.5. Let's say I put 1 inch of XPS on the outside,
Mm-hmm.
which is R5. Look what it does to the stud. It
It
doubles the
doubles.
value
Doubles the value.
at that 15% number.
Yep.
At the cavity, which was 21, is now 26.
Mm-hmm.
So for 70% of my wall, I've enhanced that insulation package. And of course, in correlation, these numbers are going to slowly rise.
Yep.
So I'll leave you with, because we'll get into this more deeper when we go on through the series in the next 201 series. But understand that cavity insulation and R value in the cavity is not the same as whole wall R value. And the example that I just gave on the outside, one of the benefits of working at Building Science Corporation was certainly working with Joe and walking around with him every day. But the people that came in to see Joe, one of his mentors, who's no longer with us, sad to say, but he's written books on building science and such. But one day at lunch, I was a young architect, a little sparky guy, and I sit down across the table from Gus and I say, Gus,
Gus Handegard.
I look around and I say, Gus, it's just me now, okay? You're the best building scientist in North America. I'm a young architect that wants to be good at what he does. Give me the secret sauce, buddy. Tell me what is the best building I can build from insulation. And in the same spirit that Joe would say, like, it's not rocket science, it's building science. Gus looked up at me and said, just put as much insulation as you can afford on the outside of the building and you'll always be building the best building.
I love it. That's fantastic.
So,
And notice it's on the outside of the building. One of my favorite Joe Stebrick analogies is he uses this sweater when you're skiing analogy. You know, if you're cold and you go outside, is it smarter to stuff that insulation between your ribs or would you put a sweater on? And, you know, I'm not saying we shouldn't put insulation in between our studs, but the most benefit long-term for that building is to put that sweater on the outside, especially in those colder climates, because you get the benefit of making sure that the entire structure of the house is warmer so that if you made a mistake and there was some air leakage or there was some ability for moisture to collect in those wall cavities, there'd be no cold surfaces for that condensation to happen. So by putting that sweater on the outside, we get a lot warmer. And remember that thermal is the last control layer. We really need that ski jacket too, that Patagonia jacket that keeps the water off. and keeps the air from penetrating means that the sweater that I put on is really going to do its job. If I go outside and shush down the slopes in just the sweater, all that air penetrating my sweater is going to get me real cold real fast. But if I put that Patagonia jacket on, now I've kept the water off me, I've kept the ice out of my sweater, and I've kept the wind from penetrating. Now I can do its job and give us that thermal resistance that we need to stay warm on the inside.
So I know we're closing it out. I'm just going to give you one quick sentence. We've done 10 episodes. We've been climbing the ladder since day one. If there's one thing I could tell you when you take a walk away from this series, no matter what you do as an architect, as the builder, you need to ask yourself, am I taking control of that situation?
Yep, that's right. And I think, Steve, you said earlier too, make every building a little better than the last one.
Make every building a little better, right? You build building 1. If you build building 2, the same way you build building 1, you failed in my eyes. You should make it you should learn a little bit more. It should be a little more airtight. I mean, there's a lot of factors, different builders, I get it, but it doesn't mean we shouldn't strive for it.
That's right. This episode of Build Science 101 brought to you by our friends at ViewRail. ViewRail is America's first choice for floating stairs and modern railings. Now tie this together for me, Steve. We've got a company that makes beautiful staircases. How does that fit in with building science?
Well, I mean, history will tell us if we build beautiful buildings, people take care of them.
That's right.
So if we put a beautiful staircase in a beautiful building, people love it, people take care of it. And, you know, I'm being an architect, I certainly care a lot about performance. Obviously, we're here talking about building science, but it has to look as good as it performs too, right? That's an equal status that we have to build as builders and architects in there. And, you know, ViewRail, they bring that to the project.
For sure. You know, Steve, I've always said that staircases are the crown jewel of the house. You know, when I build a detailed staircase, I get to show off my craftsmanship as a builder. And what's really cool about ViewRail is you may not have a 50-year-old finish carpenter who specializes in stairs in your town as a builder. But you know what? When you partner with ViewRail, they're going to build it in their factory with their excellent craftsmanship, with their precision, and then you're going to assemble it on the job. And I'll tell you what, you as the builder are going to get that feeling of, wow, this must be an incredibly well-built house. Look at the staircase, the craftsmanship, the precision. It's all there. It's really cool.
Yeah. And they got a wide spectrum of choices, right? Yeah. If you go on their website, I mean, there's all kinds of different materials for wood, different stair styles. So there's something certainly there to suit your needs.
For sure. And last thing I'll say about them, family-owned company, right in the heart, made right in the heart of America. Excellent people to work with, super friendly. They've done literally tens of thousands of these, so they've encountered every problem you might have out there, and they're really, really good people to work with. So you can learn more at viewrail.com, and big thanks to these guys for sponsoring. Guys, really appreciate you taking the journey with us. This is Building Science 101. Steve and I have already been talking about the curriculum for 201. Hopefully you'll see that in the not too distant future. Steve, great job, brother. I even learned some things today too. This is good for young builders and old builders alike.
I learned a bunch when I was putting this together with you.
It's been really, really good.
Just talking it through and the ways to explain things and the better understanding of it.
That's right. Go follow Steve and I on Instagram. Go check out our videos on thebuildshow.com. Otherwise, we'll see you next time on The Build Show.